Okay, so today we're going to look at modeling heat transfer. Um, but before we get started in looking at heat transfer, we first got to go over the physics and some of the governing equations that model heat transfer. So we'll look at specifically three modes of heat transfer: conduction, convection, and radiation. And we'll look at modeling both conduction and convection. So this is just an example of a model of a conduction through a large plane wall where it's hot on one side. So you see the temperature is 200 degrees Celsius on one side, and the temperature on the other side, it's colder. T2 is equal to 30 degrees Celsius. So whenever you have a temperature gradient like this, where it goes hot to cold, you'll have heat transfer energy being transferred from the hotter, more energetic particles to the colder, lower energetic particles. And so that's what these arrows are showing, is the direction of the rate of heat transfer. And in this example here, the mode of heat transfer is conduction through a large plane wall, and where K is the conduction coefficient, the thermal conductivity coefficient. And so this is a very simple model of heat transfer through a large plane wall. And so we're going to go over how to model that, and we'll also take a look at how to model convection as well. But before we get into the modeling, let's first take some time to review some of the physics and governing equations over heat transfer. Okay, so as I mentioned earlier, there are three basic modes of heat transfer. One is conduction, and conduction is the transfer of energy from more energetic particles to adjacent less energetic particles. Now what's key in conduction is that they're touching each other, okay? And it's being transferred and through touch of the two materials, or through a given material. The other mode of heat transfer is convection. Now, convection is the mode of heat transfer between a solid surface and an adjacent liquid or gas that is in motion. So that's important, that last part, that the fluid should be moving, okay? It should be in motion. So again, this is different than conduction. Convection has a solid surface with a fluid, like maybe air blowing next to a wall. That would be taking energy away through the air as the air is moving. Okay, that's convection. The third mode of heat transfer is radiation, which is the energy emitted by matter in the form of electromagnetic waves. So these are the three basic modes of heat transfer. In this class, we will practice modeling conduction and convection. So let's go over some of the basic equations. So heat transfer is usually denoted as Q, okay? And Q is equal to Q dot, which is the rate of heat transfer times the time. And the units for that are joules, okay? And little q dot is heat flux, okay? And heat flux is nothing but the rate of heat transfer, q dot, divided by the area, okay? So don't get these three mixed up. We have big Q dot, which is rate of heat transfer. We have little q dot, which is heat flux, which is rate of heat transfer divided by area. And then we have just the heat in joules, okay? Another important term to be familiar with is the specific heat, okay? So specific heat is usually denoted as Cp, and it's a measure of a material's ability to store heat. I'll give you an example. The specific heat of water is 4.18 kilojoules per kilogram Celsius. Compared to a metal like iron, the specific heat of iron is 0.45 kilojoules per kilogram Celsius. So you see the specific heat, or the ability of water to store heat, is much greater than that of iron, okay? Iron wants to conduct it away quickly. Water has some storage capacity, okay? So specific heat is a measure of the material's ability to store heat, okay? So when talking about conduction, okay, which remember is the transfer of energy from more energetic hot area to a lower energetic cold area through conduction, which is material adjacent to each other or going through a wall, okay? When modeling conduction, we use something called Fourier's law. And Fourier's law states that the rate of heat conduction, or the rate of heat transfer via conduction, is proportional to the area times the change in temperature divided by the thickness of the wall. Okay, so imagine we have a wall here. This is a side view, as if we cut the wall in half and are looking at it from the side. On one side we have a hotter temperature, T1, and on the other side we have a colder temperature, T2. Now anytime you have a temperature gradient like this, you'll have heat being transferred in that direction. A temperature gradient drives heat transfer. And we live in a universe where energy or heat goes from hot to cold. Okay, so the more energetic hot particles will be transferred, the energy will be transferred to the cooler, lower energetic particles, driven by this temperature gradient. So here we have a wall that we cut in half, and looking at it from the side view, and the wall is delta X. That's how thick the wall is, okay? And so if we take a look at Fourier's law, again, the rate of heat transfer via conduction, which is Q dot conduction, is going to be equal to, or let me back up, is proportional to the area times the change in temperature divided by the thickness. And because they're proportional, there is a proportionality constant. And that proportionality constant is what we call the thermal conductivity, K. K is the thermal conductivity, okay? You can think of conduction as, you can think of a train having a conductor going from one end of the train to the other end of the train asking for tickets. Okay, so the conductor will conduct his or her way through the train, passenger by passenger, looking at tickets. Okay, so again, what's important is that the material is adjacent and touching each other, and so energy can be transferred through conduction. Okay, and again, the rate of heat transfer via conduction is proportional to the area times the change in temperature divided by the thickness. And the proportionality constant is the thermal conductivity K. Okay, and the units for the rate of heat transfer via conduction is joules per second or watts. Okay, so a joule per second is a watt. Okay, so it can be expressed in watts or in joules per second. So let's take a look at this equation a little bit deeper. So again, Q dot is the rate of heat conduction, and that's going to be equal to negative K, which is the thermal conductivity, times the area times the change in temperature divided by delta X. Now this negative comes from this changing this temperature difference into a delta T, where you go final minus initial. And whenever you flip that around, putting this negative out here preserves it. Okay, if you were to multiply this negative back into it, you would end up with that T1 minus T2. Okay, but we want to put it in terms of delta T over delta X, so that we can take the limit of delta X as it goes to 0 and turn it into a derivative form. So when we do that and take the limit as delta X goes to 0, you get the rate of heat conduction is equal to negative K, which, remember, K is the thermal conductivity, and it's the ability of the material to conduct heat. Okay, remember, it's conducting heat from one side of the material to the other side of the material, times the area times the temperature gradient, dt dx, where dt dx is the slope, or is the temperature gradient. Okay, it's this slope here. So again, a steep slope would be a larger temperature gradient and would drive a higher rate of heat transfer. Now, something important here is this area. What area are we talking about? I think it's helpful to take a look at this in 3D. The area we're talking about is the area of the large plane face of the wall. Okay, we're not talking about the area here with the thickness of the wall. Instead, we're talking about this larger area of this face, this large plane surface, where the temperature, where you have T1. Okay, so that's the area that's being included there. Let's take a look at another important term, which is the thermal diffusivity. The thermal diffusivity is how fast heat diffuses through the material. So the thermal diffusivity is denoted here, and it's equal to the thermal conductivity divided by the density times the specific heat. Okay, so it's a ratio of thermal conductivity to specific heat. Now note that we have density times specific heat, and both specific heat, Cp, and density times specific heat both represent the heat capacity. Okay, they just represent it in different. CP represents it on a per unit mass, whereas density times CP represents it on a per unit volume basis. Okay, so they're similar, but just slightly different. So the thermal diffusivity is again equal to the ratio of the thermal conductivity to the specific heat capacity, which if you have a larger thermal diffusivity, what does that mean? That means you have a larger thermal conductivity. The faster the heat propagates into the medium. So remember, it's this ratio of conduction to storage. Okay, how fast something with a large thermal diffusivity will want to conduct the heat through the material faster and not store it. Something with a small thermal diffusivity will want to conduct heat slower through it and want to store more of that energy. Okay, so that's thermal diffusivity. It's this ratio of conduction to storage of heat capacity. Okay, let's go over convection now. So again, convection is another mode of heat transfer. And what's important here is that it's a mode that you have a solid that's adjacent to a fluid that's in motion. So it's the mode of energy transfer between a solid and a fluid in motion. So you can think of a wall, a solid wall, with air blowing next to the wall, and let's say the wall is hot and the air is cool, and cool air blowing next to the wall is going to take energy via convection outside of the wall, or energy will be transferred from the hotter wall to the air via convection. And we model convection using Newton's law of cooling. Okay, so and that's denoted as Q dot convection. So again, Q dot convection is the rate of heat transfer via convection. And Newton's law of cooling says that it's equal to H, which is the convection coefficient, times A, which is the surface area. Remember, A is the area of that large plane wall face, okay? And then times this temperature change between the, so Ts minus T infinity, where Ts is the temperature of the surface, and T infinity is the temperature of the fluid sufficiently far enough away from the surface. And the units for convection are given in watts. And so here's an example of what we're looking at with convection. So again, I have a wall. Okay, let's say I cut the wall in half, and let's say the Ts is the temperature of the surface of that wall, and T infinity is the temperature of the air sufficiently far enough away from the surface of the wall such that the temperature of the air doesn't change or is not affected by the temperature of the surface. And remember, the important component of convection is that the fluid or the air should be moving, okay, or flowing, and that's helping take the heat away from the hot surface of the wall. Okay, so that's convection. Also want to note here that the convection coefficient H is not a property of the material. Instead, it's typically experimentally derived. And usually it's experimentally derived based on how fast the fluid is moving, the shape of the surface, and things like that. So it's not a property of the material, but instead is experimentally derived. Okay, so this is the Newton's law of cooling, and for modeling convection. And these are so this is what we will model in this class. We'll practice modeling. I'll show you how to model on a computer. Going back to this example here, show you how to model conduction and convection on a through a large plane wall and other surfaces.